first session of the course Graph, Homomorphisms and Universal Algebra. The course is designed for students of mathematics and computer science at Technical University Dresden. Because of the Corona pandemic, we have to organize this course fully electronically. But I found it's an excellent occasion to prepare video material for one of my favorite topics. The mathematics that you will learn in this course has important applications in theoretical computer science. More specifically, it can be used to study the computational complexity of so-called constraint satisfaction problems. This is a very broad class of very concrete computational problems, and it's fun to work with them. But the mathematics in this course has many other applications. We start informally today in this session. The formal parts of this course can be found in the script, which is freely available on the webpage of the course. So what is a constraint satisfaction problem? Let's have a look. A constraint satisfaction problem that you all know is the satisfiability problem for linear equation systems. Let's start with an example. We might have the constraint x1 plus x2 plus x3 equals 1. x1 plus x2 is 0. x2 plus x3 is 0. We would like to find an assignment with values 0 and 1 so that all of the constraints are simultaneously satisfied. Addition here means addition modulo 2. So let's try. Suppose we try x1 equals 1. Now, the second constraint, it's impossible that x2 is 2 then. So the second constraint implies that x2 must be 1. And indeed 1 plus 1 is 0 modulo 2. In the very same way, x2 plus x3 implies that x3 must be 1. And here we are lucky. This will also satisfy the first constraint because 1 plus 1 plus 1 is 1 modulo 2. So this is a satisfiable instance of the constraint satisfaction problem for solving linear equations over 0, 1. So let's give this constraint satisfaction problem a name. LinEQ. It will be called LinEQ in this lecture. Let's have a look at another computational problem. This time, the input consists of a finite, undirected graph. Let's look at an example. Actually, this graph, it's a famous one. It's called the Petersen graph, but this doesn't matter. It's just an example. So the computational task is to color the vertices of the graph with 3 different colors. Luckily, I have here red, blue, and black, so that adjacent vertices do not get the same color. Let's try with this one. We start with some color, red. The neighbors should not be red. So let's make them blue. Now the neighbors of blue should not be blue, so let's try with red again. And now you see for this vertex in the lower left, in the lower right, we can choose neither red nor blue, so we have to choose black. So we can continue black. This forces a vertex to be red here. This forces another vertex to be black here, but luckily we are left with the final vertex with the color red. Alright, so apparently this is possible. So this graph, the Petersen graph, is 3-colorable. And the problem to decide whether a given graph is 3-colorable has a name. It's called the 3-colorability problem. So why is this a constraint satisfaction problem? Well, the variables are the vertices here. For each vertex, we have to pick one of 3 values. The constraints are the edges. They restrict the possible colorings. So yes, this is our second example of a constraint satisfaction problem. Our third example of a constraint satisfaction problem is called the Horn-Sut problem. Here we are again given a finite set of variables, x1 and so on, x2, and the constraints this time consist of assertions of the form x1 should be true, x2 should be true, and so on. Maybe also some variables should not be true. x5 should not be true. And then there are some more interesting constraints, which are rules of the form x1 and x2. If both are true, then x3 should be true. And another one, x3 and x4, if they are both true, then x5 must be true. Okay, so this is just an example. Let's see whether we can map the variables to true and false so that all the assertions and all the rules are satisfied. So let's start. x1, x2 must be true. That's what we know already. Now, the second line, the first rule, implies that x3 must be true. Now, x5 should not be true. It's false. Which means that not both x3 and x4 should be true, which in turn means that x4, we better set it to true. Sorry, to false. So yes, this is a satisfiable instance of the Horn-Sut problem. Finally, yet another constraint satisfaction problem that really everybody knows. It's called Sudoku. We have a 9x9 grid, and in each of the fields we have to specify a number from 1, 2, and so on up to 9. And we have to do this in such a way that in each row and in each column every value appears exactly once. Moreover, you see we have here 9 3x3 grids, for instance the upper left one here, and in each of these 3x3 grids we also have to use every value exactly once. At the very beginning, some of the fields might be pre-filled. And the task is to find a completion. We also have to fill the unfilled fields so that the constraints are met, the constraints are satisfied. You all know this, it's called Sudoku. And this is a constraint satisfaction problem. The variables are the fields, the values are the number 1 up to 9, and the constraints are specified for each row, for each column, and for each 3x3 subgrid. Every value has to appear exactly once. Constraint satisfaction problems appear in many different application areas. So constraint satisfaction problems, also denoted by CSPs, it's an acronym. Originally they come from artificial intelligence, that's where the name comes from. But these problems appear in many areas of theoretical computer science. For instance, in scheduling, in optimization, computational biology, and many more. And one of the central questions in all of these areas is, which of those problems can you solve efficiently in reasonable time? And where is this hopeless? It turns out that for the problems that we've seen, there's a quite clear answer to that. We do have a very efficient algorithm for Hornsat. And we also have a very efficient algorithm for solving linear equation systems. On the other hand, no one knows an efficient algorithm for three-colorability. So to measure precisely what it means to be efficiently solvable and to be computationally hard, there's the area of complexity theory. Computational complexity theory, we need very little from this theory. What we need is, we have to know what the complexity classes P are and what the complexity class NP complete, what this means. If you don't know, never mind, there will be a special video on that. P stands for polynomial time computation, NP complete stands for we don't have an efficient algorithm, and it's very unlikely that there exists such an algorithm.
The nice thing about constraint satisfaction problems is that they can be fruitfully studied systematically. First of all, they can be modeled in a common framework, and then a broad range of mathematical areas can be applied to investigate them. For the beginning of this course, it would be too heavy to introduce this common framework formally. So we'll not do that. Instead, we will focus on directed graphs, also called digraphs. The nice thing about digraphs is that it's very easy to introduce them, to define them formally. They are abstract and concrete at the same time. They are abstract, and that's good because you can apply them to many different settings in many different contexts. And they are concrete because you can illustrate them, you can draw them. So it's very suited for the beginning of this course.
A directed graph is a pair VE, where V is a set of vertices and E is a set of edges. So vertices can be any set. Edges are a subset of V squared, a set of ordered pairs. Let's give an example. I promised you they can be drawn easily. These are running examples, and it's important to fix the notation in the following. So a specific graph is CK, a directed cycle, so I put a little direction on top of it. It's the graph with vertices 0 up to k minus 1. And the edge relation is the successor, modulo k. So I put an edge, an ordered pair xy, if y minus x is 1, modulo k. So this is an example of a graph. So let's see an example, C3. I will illustrate it in the following by drawing the vertices as points in the plane and drawing edges as directed arcs. Another example is the directed path. So let's start again. My notation for it will be pk. The direction, it's a directed path. And here we have to be careful, there are two different competing ways of defining it. One is to count with k the number of edges, one is to count with k the number of vertices. We count the number of edges. So we have 0 up to k, so k plus 1 vertices, and we put an edge xy if y minus x is 1 without modulo. Right, so P3 would be the graph. It looks like that. Finally, I need to define the so-called transitive tournament. Here the vertices, I'll start here with 1. We have vertices 1 up to k, and we have the edges. I put an edge between I and j if I is smaller j. So it's just a standard ordering on the numbers 1 up to k. Alright, so T3, T3 would be this graph. A loop in a graph is a pair of the form x, x in the set of edges. So I'll give you an example. We have the following digraph maybe, and it could be that some vertices have a loop which we would draw as a loop, like that. Our next topic are symmetric graphs. A directed graph, G, is called symmetric if whenever you have an edge UV, you also have the edge VU. For drawing, this can simplify matters a lot. Suppose we have the following digraph. So we have directed edges between all distinct vertices. So in this situation, it's much more natural to just draw one undirected line instead of two directed lines in both directions. So this digraph we would rather draw with undirected edges. So again, there is a couple of undirected or symmetric graphs that will be important in the following. Let's start with CK without a directed arc above it. It's the undirected cycle. It's the graph with the vertices 0 up to k minus 1. And this time we put an edge if x minus y absolute value is 1 mod k. So if I draw you C5, you would have 5 vertices and undirected edges in cyclic order. The next graph we need is PK. As before, we have the vertices 0 up to k, and we put an edge if the absolute value of the difference is 1 and no mod this time. So P3 would have 5 vertices, would have 4 vertices and 3 edges. Finally, the so-called clique with k vertices. So we have the vertices 1 up to k, and the edges are all pairs of distinct elements. So in fact, it's maybe shorter and simpler to write it just like that. Whenever 2 elements are distinct, we put an edge in both directions between them. So K5 looks as follows. Now we come to the central definition of this course. Suppose I have 2 digraphs, G and H. a homomorphism from G to H is a function, H, which goes from the vertices of G, for which we write V of G, to the vertices of H, so that edges in G are mapped to edges in H. So this means if UV is an edge of G, I will write E of G, then H of U, H of V should be an edge of H. So that's, in this case, if this property holds, we say H is a homomorphism. If there exists a homomorphism from G to H, we write simply G arrows H. And otherwise, I will write G not arrows H. Let's look at that as an example. Suppose I have two graphs G and H, and I would like to know, is there a homomorphism from G to H? Let's number the vertices of H. So in this situation, I better map the middle vertices of G to 1. It's our only choice, actually, because only one has both an outgoing neighbor and an incoming neighbor. And then we are forced to map 2 to 2, this top vertex to 2, and this bottom vertices of G to 0. So the resulting map, H, I claim it's a homomorphism. And you can easily check, whenever I have an edge in G, I have an edge in the image. I have some pairs, for instance the one between these crossed vertices, that are not adjacent in G, but in the image they will be adjacent. But this is allowed for homomorphisms. So this map, indicated by the red arcs, is a homomorphism from G to H. So here come some useful observations about homomorphisms. The first is, if a graph maps to Kn homomorphically, this means that adjacent vertices in G, so vertices where there's an edge between the vertices in G, should be mapped to different vertices in Kn, because in Kn there are no loops. So this is the case if and only if G is n-colorable. Why? Because the n vertices of Kn, they serve as colors. And then the problem that you've seen in the beginning, 3 colorability, corresponds precisely to a homomorphism from G to K3. And analogously for any n. Alright, this is my first observation. My second observation is, if H has a loop, then every graph homomorphically maps to H. Why? Well, we can map all the vertices of G to this vertex which has a loop. And this will always be a homomorphism because every edge will be mapped to an edge. Remember, we don't require that there is an edge in the image if and only if there's an edge in the preimage. We only map edges to edges. Non-edges, we don't care. Non-edges can be mapped to edges, non-edges can be mapped to non-edges. Next observation. A graph is acyclic, meaning there is no directed cycle in G, if and only if G homomorphically maps to Tk for some k. And finally, this is probably more of a definition for you. G is balanced if G homomorphically maps to Pn, directed, to the directed path of length n, of n edges for some n. You see that with this simple definition, you can describe quite a variety of phenomena. Interesting properties of graphs can be described using homomorphisms quite elegantly. We continue with some observations. Note that for any digraph G, we have G arrows G, because the identity map is a homomorphism from G to G. It preserves all the edges. More importantly, if G arrows G prime and G prime arrows G prime prime, meaning that there's a homomorphism from G to G prime and G prime to G prime prime, then there's also a homomorphism from G to G prime prime. Hence, G arrows G prime prime. The homomorphism from G to G prime prime is simply the composition of the homomorphism from G to G prime and from G prime to G prime prime. So, we know that the relation arrows on the class of all finite graphs is reflexive and transitive. So it defines a quasi-order. And now we can define what it means to be homomorphically equivalent. If G arrows H and vice versa, H arrows G, we say that G and H are homomorphically equivalent. And we'll write, in this case, we'll write G double arrows H. Note that this is an equivalence relation. It is reflexive, transitive, and it's also symmetric, unlike the arrow itself. For almost all purposes of this course and all questions that we look at, homomorphically equivalent graphs behave in the same way. So this is the motivation to study the following object. Let D be the set of all equivalence classes of the homomorphic equivalence relation. And now I can put an order, and this time it will be really a partial order, on D as follows. If C1 and C2 are equivalence classes from D, we write C1 is less than or equal C2 if there exists a graph G1 in C1, a graph G2 in C2, such that G1 arrows G2. Note that this order is a partial order. It is transitive, reflexive, and it's also antisymmetric. Meaning that if x is less than or equal y, and y is less than or equal x, then x and y are equal. So this poset D is quite complicated, has quite some interesting properties, and we'll look at it. First of all, we know that there is a unique largest element in this poset, which is the equivalence class of the graph, which just consists of one loop. This is because every graph homomorphically maps to the loop, so this must be at the top. At the bottom, there is the equivalence class of the graph, which just contains one vertex and no edges. This is because this graph homomorphically maps to every other graph. In the middle, this poset is quite complicated. But one interesting thing that we can say is that it is a lattice. A lattice is a poset which has for any two of its elements a unique smallest upper bound. So if we pick two equivalence classes C1, C2 in calligraphic D, there exists a supremum and an infimum. So what is a supremum? It's a unique smallest upper bound and an infimum is a unique largest lower bound. To show you this, I have to construct this unique smallest upper bound and this unique largest lower bound, and these constructions are interesting anyway for graph homomorphisms. So let's do it. We start constructing the supremum. Suppose we have two directed graphs, G1 and G2, and we would like to construct an upper bound. The first assumption that we make is that the vertex set of G1 and the vertex set of G2 are disjoint. And then we define a new graph, G1 disjoint union G2, as the graph whose vertex set is the union of the vertex sets of G1 and G2, and the edge set is simply the union of the edge sets of G1 and G2. Now, this new graph G1 union G2 has some quite nice important properties. The first one is that it's an upper bound. G1 homomorphically maps to it, and G2 does. The second important property is that for every other upper bound, so for every G such that G one homomorphically maps to G and G2 homomorphically maps to G, we have that G1 plus G2 homomorphically maps to G. So G1 union G2 is the smallest upper bound, or a smallest upper bound, and it's actually easy to prove that it's unique with this property. Unique up to homomorphic equivalence. So G1 union G2 is unique with respect to these properties. Yeah, the picture is quite simple. Yeah? You have G1 sitting here, G2 sitting here. The disjoint union looks like the two together. And if you have a graph such that G1 homomorphically maps to G and G2 homomorphically maps to G, say here this one, then of course the disjoint union will also homomorphically map to G. You just take the union of the homomorphisms to get a homomorphism from the disjoint union. So this is quite clear. The construction to see that we have infima is even more interesting. So again, suppose that we have two digraphs G1 and G2. Now we can define the product of G1 and G2. It's called the direct product or the categorical product because it has nice category theoretic properties. It's the graph with the vertex set consisting of all ordered pairs of vertices of G1 and vertices of G2. We put an edge between two of such pairs. Let's call them U1, U2, V1, V2. We make them an edge, these two pairs, if component-wise we have an edge. Meaning that U1, V1 should be an edge in G1, and U2, V2 should be an edge in G2. This product is also called cross product, and it's easy to remember why. Suppose you have these two little symmetric graphs with two vertices. The direct product will have 4 vertices, 2 times 2, and we'll have an edge if and only if we have an edge component-wise, which means that there will be an undirected edge on the diagonal and another one here. So we see a cross showing up. So it's called the cross product or the direct product. Let's look at another example of a direct product. Suppose we take the graph P2, the directed version, and look at the product with itself. It will have 9 vertices, 3 times 3, and the edges, well, they go along the diagonal like that. So I see 4 edges. Now the direct product has some very interesting properties. The first is that it homomorphically maps to its vectors. So G1 times G2 homomorphically maps to G1, and it also homomorphically maps to G2. To construct the homomorphism to G1, a homomorphism, we can simply take the projections. So the projection to the first argument, the projection certainly preserves all edges. So the projections are homomorphisms. And we can see this quite easily in the picture. So let's see it in the picture. the first projection. So each pair would be mapped to the first coordinate. So this means all these vertices are mapped down. And now you can easily see whenever you have an edge in the product, you will also have an edge in the first component by construction. Another property is that G1 times G2, well, it's a lower bound, but it's the largest lower bound. It's an infimum. Why is that? Suppose you have another graph, G, and like the product, G, suppose it homomorphically maps to G1, and suppose it homomorphically maps to G2. Then I claim that G also maps to G1 times G2. Well, if you have a vertex X in G, we simply map it to, well, now we need names for the other two homomorphisms. Suppose the first homomorphism is called H1, and the second homomorphism is called H2. Then we map X to H1 of X, H2 of X. And it's easy to verify that this is a homomorphism. And another exercise is to prove that this largest lower bound is unique up to homomorphic equivalence. We'll leave this for the exercises. So now you might ask, what's the relation of all this with constraint satisfaction problems? Well, for the three colorability problem, this should be quite clear. A graph, a finite graph, homomorphically maps to K3, the clique with three vertices, if and only if it's three colorable. So indeed, the three colorability problem can be modeled as a homomorphism problem. For the linear equation system satisfiability problem, or for Hornsat, this cannot be modeled using graphs. For modeling it, we need more general structures. This will come later in the course. For now, we focus on graphs. The advantage is that most of what we learn for graphs will later generalize easily to the more general setting. The central computational problem in the first part of this course is given by fixing a finite digraph H. And then the computational problem is as follows. The input consists of a finite graph G and the question that eventually a computer has to decide is there a homomorphism from G to H, yes or no? Mathematically, we will be interested in the following class of finite graphs, denoted by CSP of H, for constraint satisfaction problem of H. It's the class of all finite graphs such that G homomorphically maps to H. And membership in this class is the computational problem above. The research question attached to this class is the following. For which graphs H can we classify the graphs H? For which directed, I mean always, huh? For which directed graphs H is CSP of H easy? And for which H is this problem hard? And to give this question a precise meaning, we need complexity theory. we need just a bit of complexity theory, and as I told you, there will be a video tutorial, which recaps the basics. In particular, we have to know the complexity classes P and NP complete. To give some examples of CSPs, where we know the computational complexity, look at CSP of K3. We already saw this is the 3 colorability problem. And it's well known that this is an NP complete problem. So most likely there is no efficient algorithm to solve this problem. On the other hand, let's look at an easy CSP. For instance, for h equals P1, the directed path with one edge. It looks like this. Which finite digraphs homomorphically map to P1? It's precisely those digraphs where you can partition the vertices into 2 parts, such that all the edges go from one part to the other. Why? Because in this case, we can find a homomorphism by mapping one part to the bottom and the other part to the top of P1. How can we test whether there is such a partition? Well, note that we have such a partition if and only if P2 does not homomorphically map into G. And how do we decide this? Well, this is the case if and only if there is a graph with both out degree at least 1 and in degree at least 1. So an outgoing neighbor and an incoming neighbor. And clearly such a vertex can be detected in polynomial time. So we conclude CSP of P1 is in P. And in fact, there really are efficient algorithms to decide this problem.
This course is really just a teaser for the script. So all formal stuff, all background is in the script. It's really the central part of this course. Please have a look at the script. It does not suffice to just watch the videos. Another central part of this course is the exercises. They are compulsory. You can send them in. The first series is out, it's on the webpage. Please solve it, it will be corrected and you will get some feedback. There are additional exercises in the script. You're invited to do them as well. Finally, we will also organize chat sessions on demand, but this will be organized via email. So for now, take care, stay healthy,